Oh, okay, so there are enough people. Thanks for showing up. I hope you didn't mind doing it, since today is officially a holiday that I didn't realize. So started recording. So also you should. Okay, first thing first, I want to see topics for final exam. So what I've decided is I'm spending a lot more time on predicate abstraction, although I have one other thing. I mean, obviously, I haven't been able to cover everything that I wanted to, and especially there's one other software checking method called property-directed reachability. Rather than introduce that in a superficial fashion, so what I decided to do was to cover predicate abstraction that we have already done in more detail, and test you also on that subject that we have spent. So here is some of the topics for the final exam. Okay, of course, the one topic that I have missed here is modeling. We spent quite a bit of time in how to model transition systems, and also SAT solving. And CBMC, bounded model checking, is something that you've already tested through assignments and so on. So this is what I'm going to be making questions on, and those questions will be some of them will be mostly theoretical, pencil and paper thing, and the only thing that may involve some tools is whatever that you have formulated. There might be some problems which I will ask you to formulate in terms of formulas and so on, that I might ask you to check on with Z3, but it will not involve any exercises on any verification tools, the ones that we have covered so far. So so these two the questions will be on these things, and originally I thought I'd give you more time, but now I'm wondering if because it's a take-home exam, maybe we'll limit it to having giving you one day that you can work one full day on it, and then submit it the next day, and maybe not have the whole week, which is what I had announced. So yeah, this is what I have planned. Any questions and concerns that you have?
Sir, has the exam date been decided?
I think I did say that originally I said I'll getting it out on May 9th. Okay, what I had planned. See, May 13th, which is a Friday, kinds of problem. I'm going to get the calendar out. See, the exam week is, so this is the week of exam. So what I had thought was to get the exam out on the 9th, and have it due on the 13th. Okay. Instead, what I'm saying is, I'll just maybe have it a little bit later, and you could, I'll give you 1 or 2 days to work on it, and then submit it on the 13th. Okay?
Right.
That's what I'm planning. So maybe I'll put it out on the on the 11th or so, and then have it. 13th is also the day that you will have to submit your.
So could you like do it like 9 to 12 or something? Because 13th I already have an exam. I like 2 exams.
Okay, I think I can do it. So 9 to 11th kind of a thing.
Mhm.
I'll put it out on 9th, and I may reduce the time that.
Right.
So,
So
yes.
the exam questions will be like more theoretical stuff, not the
Them
two.
will be theoretical, but as I just now said, some of the problems could be to test your understanding on these two subject matters. Okay, and they may involve you to answer it and check it on a SAT solver. Okay.
Hmm.
So some of the questions. Well, look, I cannot. Yeah, I mean, I know that we only have 4 people, but I mean, I want to get it done within that week. As I said, I will be giving it out on the 9th, and you have till 11th. So even if there's an exam on 10th, on the 10th, you have the whole day of 11th. So if I give it on 11th, then he has exam on 13th. What do you want me to do? I mean, I'll give you 2 days, but you can. I'll give you 2 days. I mean, I was intending to give only one day. I'll give you an extra day, and you can adjust with what you have. Yeah, but Dhruv, if I had it on the 12th, then Harsh will have a problem. Huh?
I have one on the 11th.
Huh? See, the reason I can give you 4 days, I mean, then I'll give you a lot more questions. Okay. What does wow mean? Dhruv is not able to speak, I guess.
Sad.
Of course, that's exam week, so nothing could be done. So that's why what I'm saying is I'll give you the reason I don't want to have 4 days because I don't know, I have to trust you guys. I mean, the longer I give, I have to make more questions, okay? And you will have to then mix and match, okay? So I can give you 2 days for you to work, and if you have exam on one day, you have the other day. Huh?
Sir, like, is it possible that we could have it slightly after, just after like exam week 14th or 15th, something like 15, 16 or something like that?
That we can do.
Because like,
I don't want to
But
push
people will have like trains and flights.
What?
People will have trains and flights. We have to leave the people at hostel will have to leave the hostel.
oh,
No,
you're
those exams are take-home exams anyway.
No, so if it's 2 or 3 days, then like it will be a problem.
What?
like we can.
If someone is in train, then the train might take 2 days.
For travel. If you're traveling, you mean, huh?
I think the 9, 10, 11 plan is fine. Like 1 day exam and like the questions what 1 day exam and you have 2 days to do them.
Yeah, you can do that. Yes.
Yeah, I guess we can also do that.
So what's the deal? So I'll give it out on 9th and make it due on 11th. Huh? Is that okay?
Yes, yes. Unless someone has like exam on both days, 10 and 11, then I think you should make a Moodle post on this so everyone can answer.
Yeah. Well, what's the? I didn't understand why you're against. So there is exam on the 14th also, is it?
I think I might have a exam on 14th. It's not clear yet. So
yeah, then we'll be moving. So your suggestion, Harsh, if Harsh was the guy, so it was to have from 14th to 16th, is it? So who else are here? Diganta is here as well. So Diganta, you can throw your 2 cents worth as well. So Sandeep is not here. Yeah, I think it's better to finish it off. 9th to 11th or 10th to 12th. Okay. Give it out on 10th and do on 12th, or give it out on 9th. Because otherwise you have exams in someone or the other exam. No? So 9th to 11th is okay, everyone?
Yeah, 10 to 11 is fine with me.
10th through 12, you mean?
Yeah.
Oh, okay, 10th to 12.
Yeah, so the exam will be for 1 day and like you're giving 1 day buffer extra day or something.
Yeah. Okay, 10th to 12th. Okay, Sandeep will have no veto rights because he didn't show up. Okay, so 10th to 12th. Okay, because I heard some kind of complaining tone from 9th to 11th. So 10th to 12th is okay. Yeah, so I will do 10th to 12th.
So like, so exam you will set for 2 days and 1 day is extra, right?
I'll set for 1 day, you can take 2 days.
Okay. So it will be like for 2 days then. Okay. Makes sense.
Okay. Yes. So this is big enough. You know, see, I have some problem with my laptop. So there are portions on the screen I can't see. So if I put it on full screen mode, I can't see a lot of the slides. And when I can't see, I can't speak. That's why I'm making it this way. So is this big enough for you? Yes? No?
Yes.
I'll have to get it to this size because otherwise I can't do. Okay, so last time I ended with the CGAR procedure, the counterexample guided abstraction refinement procedure for checking, for verifying using the, which is, using predicate abstraction. Okay, so we've spent quite a bit of time in, explaining how predicate abstraction, an abstract model is constructed based on a given set of predicates. Okay, so here's the steps. So now I'll illustrate it on a few more examples. So for the benefit of people who might didn't show up last time, and also to give you an opportunity to ask questions. So first is to determine a suitable set of predicates. Okay, and these predicates, as we pointed out, should be property directed, and you look at the atomic formulas that appear in expressions in the program, as well as those that appear as atomic formulas in the property. And that is, or some subset of them, you choose them as predicates. And you construct the abstract model. We have been doing it eagerly. By eagerly, I mean you construct it once and for all. Okay, the complete model. There are, usually tools don't do it eagerly, because constructing the abstract model is expensive, and sometimes they do it lazily, by which I mean they do it on a need basis, construct only partial model and so on. So, but those are for details, that we won't get into. So once you have constructed the model, now your model will be a finite model because you are working with a finite set of predicates, and your states are different valuations
for those finite set of predicates when they are evaluated on the concrete states. So now you've reduced it to a finite state model, hopefully small enough that you will model check, okay? Based on the way that you computed fixed point by propagating the post as you saw on the abstract. But I'll show how that works for a predicate, on a model that is abstracted based on predicates. Okay, and exit with success if the property is successfully verified. Otherwise, you exit with failure. In the case of failure, you will generate a counterexample trace. Okay, that is yes. If the generated counterexample is not spurious, if that's real, then you declare failure. Otherwise, if it is spurious, then you go and then change your, refine your abstraction, by which I mean that you'll have to change the predicates, on which that you base your model. Okay. So yeah. So there are various questions. I mean, well, how do you even check the abstract model? That I will illustrate. How do you check if a counterexample is spurious? Then various things. How do you analyze the counterexample? And finally, the toughest question: how do you fix your predicates to refine it? And those are some of the things that we will look at, especially the first three bullets here. How do you determine what the new set of predicates? So that's a hard problem, and that we will not get into. So before I get into the details, so I just want to, just to get you into the thing. So predicate abstraction. So as you know, it's parameterized with respect to a set of predicates. Okay? Each predicate is defined over concrete state domain values, and an element of the abstract domain is valuations for these predicates. So so it will be, you can view them as bit vectors, where each bit says whether a particular predicate evaluates to true or not. So if you compare it to, when you do abstract interpretation, we define the abstraction function over sets of states. Whereas here, when I introduce predicate abstraction, alpha, it maps a particular value. And so I've made up alpha just to compare what this, when you can lift this alpha to sets, set of states in the obvious sense. And then you will see that this existential abstraction, which is how we define the predicate abstraction, also has a corresponding Galois pair. Okay, with the alpha, use alpha. You can lift alpha to over sets of states, and then there's a corresponding gamma. So that way you can actually see how you can relate it to this, how abstract, you can view this predicate abstraction as another form of abstract interpretation as well. So this alpha, when you want to extend to states, it is defined over sets of concrete states, and it maps to sets of valuations for these different possible valuations for these predicates. And it's defined as, given a set of concrete states, it has all those things. If there exists a value for which it has all those valuations, if there exists one concrete state in this set X, such that for which this valuation, a particular valuation, is true, then that is included in the abstract state. The corresponding concretizer, picks the largest, okay, of all the largest state that you map it back to the largest state. Okay, so given this works on so as a set of Boolean valuations for these things. A set of states can always be viewed as a predicate. So here the predicate is over these proposition variables, where one proposition variable corresponding to each predicate. Then the gamma, given any set of abstract values, that gets mapped to all set of all concrete states for which that predicate, the abstract predicate, is true. So, for example, gamma of the abstract set of states 1, 1, 1, 0, assuming there are two predicates that it is based on, is really the set of all concrete values for which this formula P1 and P2, or P1 and not P2, which is what these two things correspond to. So that's how you view it on that thing. Since we are picking the largest among those things, that's why when viewed this way, alpha gamma, this predicate abstraction also forms a Galois connection. So here are some examples that I've chosen. Let's suppose that your concrete states is pairs of integers. That's my concrete domain of states. And there are two predicates that I'm tracking to construct the abstract model. P1, which corresponds to x being greater than y, and P2, which tracks whether x is equal to y. Then alpha alpha, which is on sets of states that contains all values where x is not equal to y, will map to 1, 0, and 0, 0, right? So because if x is greater than, if P1 is 1, that means x is greater than y, then the second one has to be 0. So therefore, it maps to, the pairs such that x is not equal to y can be either such that x is greater than y, or x is not greater than y. So it maps to these two states. Similarly, alpha with such that x is equal to y plus 1. Since you know that x is greater than y, it always maps to is 1, 0. And so does this set of states where x, every element of the pair is such that x is equal to y plus 2. And that's why this is an abstraction. So it can map different set of states to the same set of abstract value. Okay, so both of these are mapped into a set of states where x is greater than y, and that's where you lose some precision. Yeah. Similarly, suppose you had x is not equal to y. You already saw that it is 1, 0, 0. And if you had the set of states where, set of pairs where the first x is even, the other one odd, that also, in terms of these predicates, you can only represent it as 1, 0, and 0, 0. And that's why, with a given set of predicates, since if they don't match with particular predicates that you have, then there is a loss of information. Okay? And similarly, you can have gamma mapping to this. So the top element will be, will get mapped to all possible pairs of integer. In particular, 1, 1 is not feasible in the concrete state because you cannot have x greater than y true and x is equal to y to be true, and that's why 1, 1 will get mapped to the empty set in the concrete thing, and so on. Okay, so whenever there is multiple values getting mapped by alpha alpha to the same thing, then your gamma will pick the largest among them. So that's why these two pairs are Okay. Okay. So, any questions there? Yeah. So you need to get familiarized with how sets of states get mapped by these predicates in order to really understand what it means to model check. When you do, check, verify a particular property in the abstract, what it means, what that means in terms of the results on the concrete state. So, since I won't use that example, okay. So what do you, like I said, so in order to do this model checking on the abstract state, you have to construct the transition relation on your abstract model, and we saw some examples where a transition relation was constructed, and then you have to construct a post based on given a particular transition relation, and that post is what will be used to propagate. Okay, when you do the check, when you verify, just like you did in the algorithm that you use for abstract interpretation. So here I'm going to show you how it works on real programs. Okay, so what we have is given, say, I have using a different example. So that example was same thing that I used for this one. And you saw this program. I'm going to exactly show you how, although I've shown this in this thing, Daniel Cronin showed it as a Boolean program, there is a transition relation and a post, okay? And this one, this particular Boolean program is you can say that's a representation of your transition function. So this one is based on two predicates that tracks whether I is equal to 0 or I is even. And I'm constructing the transition relation, and I will relate this Boolean program to that. Okay, so that's what I'm doing here. So your post will be defined with respect to a transition. Okay, so given it's calculating the post by constructing corresponding to the abstract transition relation given a set of abstract states. Abstract states in this case are 2 bits corresponding to the valuation of P1 and P2. It is the image of this set of values in X under T. So which means, so it has for every pair predecessor pre-state P1, predecessor state P1 P2, the predecessor of P2. So it maps if there exists an element inside X in the pre-state, and it is true of any P1 P2 such that that predecessor gets mapped to P1 P2. So that's how image is calculated. That you do here explicitly by taking the existential quantification. Okay, remember that the post in the abstract interpreter was also defined as an existential, but you didn't have to really use the existential quantification elimination, because there you relied on for example, an interval domain, you used the you had certain functions in terms of the parameters. Okay, so whereas here you have to explicitly define it as a predicate formula, and then compute the post by actually eliminating the existential quantification to derive and represent it as a formula. So here, since it's these two predecessor states corresponding to P1 and P2 are being existentially quantified, this is this formula is equivalent to the following quantifier-free formula. So which is effectively, instantiating this precursor P1 and precursor P2 to the different possible combinations. So 0, 0, and then you instantiate that for 0, 0, or x all the way to x, x1, 1. And just like, and then you will have to, if you want to apply it to a program, for every basic statements in your program, you will have to define a corresponding post, and that you can do in a generic fashion using this. After you have defined the transition relation for each of these things. So, for example, for I is equal to the assignment statement, I is equal to 0, the image over some x will be, if I is equal to 0, then your post, if I is equal to 0, regardless of what your predecessor stated, is I gets assigned to 0. When I gets assigned to 0, automatically P1 becomes true, okay? Which is because I is equal to 0. And 0 is even, so it gets mapped to P1, P2, okay, correct? So regardless of what your pre-state is, whether it is 0, 0, 0, 1, or 1, 0, 1, 1, it gets mapped to P1 or P1 or P2. So that's why this will be a formula of this kind. So here I'm actually, first representing the transition relation corresponding to I is equal to 0, and then using this post formula here to, after elimination of the qualifier here. Okay, so, and similarly, for example, for I is equal to I plus 1, so what will happen when you have I is equal to, when you make I is equal to I plus 1? If I is even in the pre-state, certainly it will not be even in the current state. So you will have to do it for each of them. So if it is 0, 0, that is if I is not equal to 0, then you can have so if I is not equal to 0, then it will be a P2. Otherwise, because if I is not equal to 0 here in the next state, you can either have I is equal to, since it's not even, it's not even. So the next state, all you know is that it has to be even. Therefore, that's why P2 is true. But you can have I is equal to 0 or I is equal to 1 in the next state. And that's why I have defined it this way. For all other things, you can work it out. So by the way, 1, 0 is not feasible here at all, correct? So that's why I have not shown what it maps to 1, 0. So if I is, because if I is equal to 0, if, what is on 0, 1? No, 1, 0 is not correct. If I is equal to 0, then it has to be even. That's why 1, 0 is not a feasible state in the concrete, and that's why I'm not shown what these things map to. Okay, so when you construct your abstract model, this is what you'll have to do. If it's a software program, then you will have to for I is equal to 0. So you can construct. So regardless of what your pre-state is, it will be P1, P2. If I is equal to 5, then if the assignment assigns 5, then it will be, then you know that, for example, it cannot be, presently it is not 0. Regardless, the next state, I cannot be 0. That's why P1 is false. And I cannot be even either, and that's why that thing is false. So, when I is equal to I plus 1, as I've shown, this is the actual formula representing the post state for any given set of abstract states XX. Okay, so each disjunct here, it tells what the successor state should be for that particular valuation. So that's what I'm doing here. And you can see that you can also have, so in this in this program, so that I showed you earlier. Yeah, you saw this program. So this is what it was being done. And I posed the question if this is minimal or not. What is being shown here, these post definition, the definition here is based on a transition relation that is minimal, okay? And minimal one will have to consider these possible valuations for both P1 and P2, and you'll have to define it. And that's how at the next state is considering both the valuation of both the predicates in the pre-state. And whereas here, so then you will have to consider your, if you were to express it as a Boolean program in this fashion, then a minimal one will have to do a case analysis based on P1, P2, the valuations for pairs of predicates. But as a simplification, this Boolean program that is being done here is, it only defines it. It's really an over approximation of the minimal model, because it is, only considering for each, assignment to P1, each assignment to P1, which determines the next value, is based on just checking what the previous value of P1 alone is, okay? So that's why, and in particular, you will see that this is not minimal in the sense it is adding, it is an over approximation to the minimal abstraction. A precise abstraction would have to capture, would have to be a case analysis, for example, based on both the predicates. So for example, I have defined here for I is equal to I minus 1. So you have to do a case analysis based on both valuations for the thing. So which means you will have 2 to the 2 valuations here. And sometimes that, if you find that to be too onerous and too expensive for you to do, then you can do, this is, like I said, you can add more states and more transitions to your abstract model, and that's what is being done, here. So, in other words, what I'm saying is this is what is being constructed, but sometimes, some tools will just directly construct these transition relations from a C program and work on that, and some tools they construct equivalent a Boolean program, okay, representing the abstract model, and that's the illustration that I'm showing here. But for analysis purposes internally, you will have to construct this transition relation and a transition relation and the corresponding post, and you can have over approximation of that if constructing this the formula, the precise formula, which corresponds to the minimal abstraction is too expensive, okay? And that's what is being done here. So any questions here? So as an exercise, I want you to do this. Here I've thrown another variable j. Okay? There was a question in one of the previous classes, I think by Chandradeep, I think. What if you have an arbitrary expressions on the side? Okay? Which in this case, I have a variable j, which is not being, the predicate being tracked is oblivious to values over j. And so you will see that you cannot, your transition relation, that the best transition relation that you can get, since it is forced for you to express in terms of these predicates, it will be, it will be too coarse. Okay, so you know that If I is equal to 0, then you can use the same thing. If I is equal to 0, regardless of what j is, that's why for I is equal to 0, when the first bit is 0, that is P1 is 0, then you can somewhat precisely capture it, okay? Since you know that it is 0. So this transition relation correspond to exactly I is equal to I minus 1 for x is equal to 0 and x is equal to 0, 1, okay? But for x is equal to 1, 1, when it is, when I is, when I is equal to 0, you can capture it precisely. When I is not equal to 0, you cannot. I will let you review this on your own, okay, to see if this is the best that you can actually get, okay, and that's how that you'll have to do. So the process is, first you have to define a transition relation corresponding to this in a minimal way. So, and this is how you do. The criteria is this. And then to calculate post, you have to do an existential quantification elimination, which is done using in a formula wise, this is what is represented, but there are more efficient ways to represent Boolean formulas. One particular thing is to use BDDs to we have not got I've not introduced BDD in this class, but they are kind of a canonical representation where doing this existential quantification elimination for any particular x can be done fairly efficiently, without. So if you use CNF notation, which is what I'm using here, there's automatically will be a blow up. But there are other representation that can be used in which this elimination can be done. Quantification elimination, existential quantification elimination can be done in linear time over the size, and the resulting formula that you get after you eliminate the thing in as BDDs can also be compact, and that's why this kind of model checking or using predicate abstraction is still usable in practice. Okay, so how do you deal with guards? Okay, as you saw. So here, in order to do this computation, you will have to do two things. One is you have to compute the post, and that's what I've showed you. For each statement in your program, you have to do post. And so there'll be branching based on guards, and you will have to now define how you abstract the guards as well. And that's also done. The criteria that is used is similar to the way that you did in the case of abstract interpretation. Here, we are just using it over sets of predicates, okay? So given a guard G, a post G, question mark, thing, so post corresponding to the guard will be defined as an over approximation. It over approximates the set of states, set of concrete states for which G question mark is true. So you will have to define it such as it should return an abstract formula such that, so it must certainly include the concretization of this should certainly include all the states for which G question mark is true. So this is the criteria that you will have to do. If there exists even one state which gets mapped to P1, P2, okay, then it gets mapped to P1, P2, and that G question mark, predicate is true for that state, then this should be included in the set of abstract states that you propagate. Okay, So that's how that you will define. So and this is how it was done in while we did abstract interpretation too. So for example, and similarly, if you take the negation, that over approximates the set of states for which not of G question mark is false. Okay, so that's why. So you have to define what the post operator is for both versions of these predicates, because both are over approximation. So the over approximation for the negation of a Boolean expression cannot be just the complement of the set of states that G question mark is marked. So therefore, you will have to do it individually for G for the positive version as well as the negative version. Okay, so let's see some examples. So suppose my guard, the concrete guard is I is greater than or equal to 2. Okay. So if I is greater than or equal to 2, you certainly know that P1, so states that satisfy I greater than or equal to 2 in the abstract state should be such that P1 is false, right? Because P1 represents I is equal to 0. But you cannot say anything about the other predicate. Okay, so that's why. So P2 can be either true or false. Similarly, the negation of I'm sorry. This should be I less than or equal to 2, not negation. This I. Let's see. So if I don't know if I meant to. Let's see. So if this is I not this is not not I less than or equal to 2. So I should, if I is greater than greater than 2, then you can, it will be P1 or so it is, let's see, so I think I'm representing I greater than 2. Negation of I think this should be read as I negation of I greater than or equal to 2, not less than or equal to 2. So greater than or equal to 2 means I should be less than 2. Okay. Negation of, read this as negation of I greater than or equal to 2, which means it's representing I less than 2. So if I less than 2, there are states in the concrete for which P1 is I less than 2, for which I greater than 2 is false. Therefore, P1 can be true, and there are also some states where for which it can be even. So this will be P1 or P2, and that's how you will have to define. Okay, so use this criteria. So in order to define the tightest, the strongest predicate in terms of P1 and P2 that expresses this an over approximation of these things, and this has to be constructed just like in the case of abstract interpretation. You did it for all operators and so on. You will have to do it here as well for every Boolean operations over those things, and then they'll have to be considered in terms of predicate. Similarly, I've shown you, for example, prime of I and not of prime of I. So if I is prime, see, obviously, these things will be very coarse in terms of these things. When you see these predicates, that's why I'm saying that your choice of predicate will have to include, if these things appear as Boolean expressions in your program, you better include these predicates as well. If you don't, you will see very coarse abstraction of these, of these things. So, for example, if you know that I is prime, the best you can do is, if I is prime, you know that I cannot be 0, because prime is defined as something greater than or equal to 1, a positive number. So you can say that not of P1 is true. And if it's prime, it cannot be even. So prime I can be, relatively accurately expressed. If it is not of prime of I, you cannot say much about it, and you will have to, throw your hands and then do, include everything. Similarly, star is something which is used. It's a non-deterministic thing. It can be either true or false. And sometimes when you write your programs, it is as Boolean programs, you may want to just abstract your Boolean expressions, to the coarsest thing, by saying it can be either true or false. I don't care. Okay. So in that case, you can have both. You can replace that with star, in which case star is abstracted into just true. It includes all the states, and negation of star will also be true. Okay? So this is what you will have to do in order to construct your transition relation and your post for each assignment statements and your expression. Okay. So once you construct with the guard, as you know, when you actually propagate sets of values during this fixed point calculation, you will have to take the conjunction of these predicates that define the guard and conjoin that with whatever the current set of states is at X. The current set of abstract states is, and that's what X is, and that will be a predicate. Okay, and so any questions so far? Okay, so let's see how this thing works. Once you've constructed the post and some guard, then you can pretty much use. So here the post and your guard were, elements of some abstract domains with a certain shape, like intervals and so on. Whereas here, the difference is that your abstract set of states are represented as actual propositional formulas. Okay, and that's the only difference. Okay, and your fixed point equation will start with the same thing, and your fixed point equation here will be involve post. As defined, as I've shown you with the define, and instead of join will correspond to union, which is OR, okay, disjunction. And similarly, meet, which we will use when you compute fixed point, greatest fixed point, descending, on a descending chain. When you will use meet, that will correspond to a conjunction. Okay. So since we are dealing with propositional formulas here, join is a union, and meet will be intersection, which is intersection of formula or a conjunction. So, and that will be clear. Let's take this first. Let me do not the prime example. So we'll do this one. Okay, this example corresponds to the program that I've shown here. Okay, this is the program. So this CFG here corresponds to this program. Here. So I have. I'm sorry, it is this program here, okay? This C program, here. So I start with L0, so where I can have I be any possible abstract values. I don't include 1, 0 because that is not, that's an infeasible, that corresponds to an infeasible concrete state. Now, you could throw in 1, 0 also, but you will get you will get a lot of spurious states. Okay, so you can choose to, I've defined all these these post value that I showed for these statements here, such that I not equal to 0 is not include this 1 0 state is not included. Okay, but of course you can include that, and then you can have arbitrary transitions from that as well. Then that will be not a minimal model. Okay, so you start with that, and then as before, so this CFG, so you do an I is equal to 0. Okay, and then you get L1, which corresponds to the head of the loop. Then you take a transition corresponding to the loop condition, which is a guard. If that is true, then you get inside, and then you do a transition corresponding to executing the body of the loop, which is I is equal to, this should be I plus 1. Yeah, this should be I plus 1. Well, I don't know if I've done I is equal to I minus 1, I plus 1. Let's see. So you do that, and then you go back. This arrow, this edge should be arrow on the other side. Okay, you go back there. Now, or you exit when it is not even. And how do you model check? Just like you did, with with you did here. You start by initializing all of them to bottom. Okay. And then you will propagate things, okay, using the post, because a post is like a predicate transform. Okay, so given a formula which represents the pre-state, in this case it includes 0 0 1 0 1 and 1 1. It then applies this post and uses the same algorithm. Okay. And so you saw the post for I is equal to 0 had only P1, P2. Therefore, what you get here will be from bottom will be improved to 1, 1, 1. Okay, because that was the post corresponding to I is equal to 0. Correct. So that was the post corresponding to yes, I is equal to 0. It was P1, P2. Yeah, for I plus 1, it was not P1, not P2. Okay, so as you can see, so that's what I'm propagating here. So bottom becomes 0 0, and that's okay. This is the program doing. So similarly, P1, P2. So I is equal to 0. So it will be 1 1. That gets propagated. So even I is a P2. So you have to take a conjunction of 1 1 and P2. So that will give a 1 1 here. So because even of I, so that gets propagated faithfully. So that gets 1 1, and then you do the post on this to corresponding to the post defined for I minus 1. So here, since you have 1 1, you will have to do so. You have to apply. So this was the post for I is equal to I minus 1. So for x 0 0, this is the complete formula. So here you have to apply this to your predecessor formula, which has only 1 1. So the 1 1 case gives rise to not P1, not P2. Okay, so you get just the singleton set 0 0. So bottom gets improved to 0 0. Now that you a union, right? You take the union of this and this at this location. Okay, and therefore what you 1 1 will get improved to. We'll add 0 0 also into this. Okay, and then you will see that from there you won't none of these locations L2 and L3 will have any improvement. So not of even if you becomes applicable here, because it's not of P1, P2, not of even corresponds to not of P1, P2. And since 0, 0 has been included, you can, this exit path becomes feasible, and you get only the result of constraining this set to 0, 0, and therefore you get 0, 0, okay, which is accurate for that particular program, because when you get out, you know that your predicate is not even, and since you have done I is equal to I plus 1, here it is not 0 either, and so you do get the precise result. So here you have not lost much information. I've also shown here for the example for prime, okay, and that is you will see that there is significant loss of information there. This is just implementing the same thing corresponding to with the the post corresponding to the guard prime, and you will see that because not of prime is the representation of not of prime in terms of these predicates is too coarse, you will get a fairly coarse over approximation of the thing. It will include not just the feasible state 0, 0 here, but also 2 other additional states, okay, which makes it too coarse and not able to verify. And so you will have to do prime. You have to, that one way to fix that is to change the predicates to include prime also as one of the predicates. Okay, so I will just take maybe I'll stop here rather than rushing it through. So what I will discuss next time is these, this part. Okay. So we covered, how to do abstraction and construct the abstraction, how to model check. Okay. And next time, what I will explain is how to check what is spurious, if a particular thing is spurious or not, and then how to analyze the spuriousness. These are the 2 things that I will cover next time, which I expect you to follow, because there will be questions on that in your final exam. That I will cover in the last class. As to the problem of how you refine the predicate based on the analysis of the counterexample, that's a harder problem. That's actually a synthesis problem. I wish I had time to cover the synthesis problem, which I do not, and therefore I will only give an idea of how to do that, but I will not include any questions on the refinement of abstraction. But certainly analyzing this spuriousness check, I will include. The real thing is every step in here can be done. Here will need the service of a SAT or an SMT solver. Okay, so that is one of the distinction. Okay, things. So here, since you're doing it on propagating, your model is in terms of predicates, actual predicate, precise predicates, and your propagating formulas. With those predicates, you get a fairly accurate set of states. Whereas here, the idea of static analysis, one of the reasons that it is so efficient and it scales much better than these things is because then your post operator was implemented, did not need to use a SAT solver at all, because you only used certain, you relied on operations on the parameters of the domains. For example, in the case of interval domain, low and upper bound, how you implement the join, meet, everything in terms of simple algebraic operations over those domain. And that's why you don't need to use SAS solvers. And that is the idea there. But that might result in some cases, a lot of precision, there is value to be added by propagating precise predicates, and that's what this thing does. And all these things can be done using you need a SAT solver to do, and we will discuss how how these things, each of these problems can be expressed as a instance of a query to a SAT solver. Okay, constructing the post I've already indicated, I've already described. Similarly, for doing these two things, checking if it is spurious and how to analyze, I will explain as to how you can do it as using the SAT solver. Okay, so I'll stop here to take any questions you might have. Okay, I urge you to attend Thursday's tutorial, as we want to get a status check on your status of your progress on your project. And we'll also, I'll give you a criteria on which we'll be evaluating your project outcome, okay? And what is the minimum thing that we expect, and what are the criteria on which we'll be evaluating all the tasks thing. And we'll provide you with some more technical information about the task and some doubts that you may have, and we can get it clarified. And that is for Thursday. So I encourage you to attend Thursday and Friday. If you can help it. Yeah. Thank you.